Hi, this is Mattino. Today, we are going to talk about USB. Fact: USB was developed in mid-90s, but became popular only in the early 2000s. The standard was pioneered by IBM, Compaq, Intel, Digital, Microsoft, NEC, and Nortel, who, for that purpose, established a non-profit foundation called USB Implementation Forum, or USB-IF. Although back then, computers were already equipped with ports that sort of acted in place of USB, the need for the new interface was long overdue. So what was wrong with existing ports? Well, first of all of them were originally created with specific devices in mind. For example, the keyboard port was designed to work only with keyboard and didn't really support any other peripheral. Another hardware port, the LPT, which stands for Line Print Terminal, was intended for connecting printers. It was a parallel 8-bit interface, meaning each byte of information would be represented by a combination of ones and zeros on its data lines. To synchronize the sending and the receiving parties, the strobe signal would be pulsed as each byte of data would have been sent. So, if you intended to print, for example, the word hello on your printer, your PC would send this data block onto its LPT port. The LPT, in fact, was pretty popular with electronics hobbyists because it could be utilized to control multiple external circuits like transistor switches or resistor-based DA converters, so it was sort of versatile. There even used to be a DIY digital-to-analog converter device called COVOX that could be used in place of a sound card in case you couldn't afford one. The LPT, on the other hand, had a whole bunch of disadvantages. In the first place, it had no galvanic isolation whatsoever, because its lines were mere TTL outputs, which meant you couldn't hot plug anything into it. Second, it had no power supply lines, so to power an external device, you either had to use an AC wall adapter or the keyboard port. Third, the LPT could not read data in parallel mode. It did have a number of TTL inputs, and they could be configured for reading, but the compatibility across systems was pretty poor, so basically, it wasn't very usable for data input. Another very popular interface back then, and we really must mention it today, was the famous COM-porт, a serial bidirectional bus based on the RS-232 protocol implementation. Ones and zeros in RS-232 were encoded by different voltage levels, where negative voltage down to minus 15 volts corresponded to a logical 1, and positive voltage up to plus 15 volts to a logical 0. This encoding method made it possible to increase the maximum allowable cable length up to 15 meters, that's 50 feet. To implement this functionality, at the motherboard, the interface was powered by a bipolar power supply. That's why all ATX power supplies nowadays still carry the minus 12 volts power rail. We could say that in a way, this serial port was a predecessor of USB, because it was much more versatile than LPT, and could be used with a wide range of devices, including mice, modems, plotters, and also some dedicated professional hardware like CNCs, medical equipment, photo printing machines, etc. The COM-port used serial method of communication, meaning each byte of data was split into bits that were passed over the data link one by one. The port could simultaneously transfer and receive data. For that purpose, it had two separate physical lines called TX and RX. The so-called stop bits, or software flow control, were used for synchronization. It should be noted that the RS-232 protocol successfully survived to this day and is widely used with microcontrollers. Thanks to its huge popularity, its support libraries have been written literally for all platforms in existence. Modern circuits like Arduino, for example, however, mostly use its TTL-level version, So if you got hold of some old hardware like a modem or plotter and would like to interface it with Arduino, you have to use an RS-232 level converter with a bipolar supply. The COM-port, however, never had pins for powering external devices. So the developers had to come up with all sorts of tricks for that purpose, like use additional port signals and wire them together to increase output power. Another obvious and huge disadvantage of the COM-port was its slow data transfer rate, insufficient to run even a regular printer. As a result, the developers were tasked with creating a brand new high-speed universal data transfer port. It had to support hot plugging, needed to have lines for powering external devices, and must have been effectively protected from interference and failures. The new port also had to support plug-and-play and work with it in real time. Also, apart from the data exchange protocol, it was necessary to develop the physical design of the connectors, because DB-type sockets popular back then did not meet the requirements and ideology of USB. One of the key points of USB protocol is that it does not allow peer-to-peer communication. Every USB connection always has a master and a slave device. Master is also called the host, and slave is called the device. These terms can be used interchangeably. USB standard also does not allow connection of several devices in parallel. For that purpose, a USB splitter or hub must be used. In most cases, computer acts as host, while printers, scanners, cameras, USB flash drives, Bluetooth adapters, USB keyboards, etc. act as slaves. Because this ideology was initially the basis of USB standard, it was also reflected in the design of USB connectors. The one that connects to the host is called USB-A, and the one which goes to a slave device is called USB-B. The connectors and sockets are specifically built in such a way that when inserted, the ground wire closes first. This is what USB-B looked like initially, and like this, it survived to this day. You can find it in printers, USB audio interfaces, MIDI keyboards, external hard drives, and also the Arduino. When USB finally made it to mobile devices, the market needed more compact connectors, so the very first one developed was called Mini USB. The Mini is pretty rare these days and can be mostly found in car GPS navigators and cameras. When the mobiles became even more compact, the micro USB was introduced. Nokia was one of the vendors to pioneer this connector. Still, many manufacturers kept installing proprietary connectors into their devices. Chinese manufacturers sometimes would even use different pinouts for connectors of the same type. Needless to say, all this brought great inconvenience to users. Please note that both Mini USB and Micro USB are still variations of the USB-B connector. Their full names are USB Mini-B and USB Micro-B respectively. They are electrically identical and only differ in shape and dimensions. At this point, there are 4 versions of USB protocol out there. All of them are, of course, backwards compatible with each other, meaning you can insert an older device into the socket of a newer version. USB 2.0 is still most common today. It's supported by the vast majority of USB devices around the world. And by the way, iPhone 14, which is the latest at the time of filming this video, also supports only USB 2. Compatibility is ensured not only at physical level, but also at logical level, meaning that the device will power up correctly and establish a connection with the host. Such compatibility is ensured by 4 signal lines, 4 wires, which are present in absolutely any USB port, starting from its very first version. Here is a diagram of a standard USB cable. The negative power line, as usual, is designated GND, ground, and is the black wire in the cable. The positive power line, V-bus, is the 5 volts. The color of the wire is red. The two remaining lines, D+ and D-, are responsible for data transfer and are made into a twisted pair. Their colors are green and white, respectively. The USB cable also has a shield connection designed to protect against interference. It connects to the metal frame of the connectors and is grounded at the host side. Please note that in practice, if you're trying to build something from a salvaged USB cable, you cannot rely on wire colors, because Chinese manufacturers often use non-standard coloring. The pinout, however, will always be intact. And by the way, here's how to remember it. If you hold the USB-A connector like this, you'll have ground on the left, then goes the D+, remember, positive goes first, then D-, and eventually the 5-volt supply. You should keep in mind, however, that in some USB devices, the metal frame can be connected to the ground line. Please consider that when checking cable for continuity. Looks like all USB magic is happening in the D+ and the D- data lines. So, how do the USB devices exchange data? The key point here is that USB is the interface with a single data line, meaning that it cannot transfer and receive data simultaneously. The two physical signal lines made into a twisted pair comprise the symmetric or balanced connection, which is a signal transmission method widely used in communications and also professional sound equipment. You have probably already heard this term. So what's a balanced connection and how does it work? Consider the two diagrams here. In both cases, the power source is the BAT1 battery, and the receiving side is the VM1 voltmeter. A DC source is used here intentionally, because digital signal in a USB cable basically consists of DC levels that change with time. The difference between these diagrams at first glance is insignificant. However, if you look closely, you will notice that in an asymmetric circuit, the negative line is connected to shield and grounded, and the shield, in fact, acts as one of signal lines. In the balanced version, the shield is also grounded. However, it is not connected to any of the signal wires, and they are basically free and equal to each other. And by the way, that's why the connection is called symmetric or balanced. Now imagine our cables are affected by interference. What's going to happen then? The wires will be affected by magnetic field, and EMF will be induced, which will cause the signal to be distorted. That's basically what interference is. Essentially, the cable in this situation behaves like a transformer winding, which, affected by the magnetic field induced by the core, generates EMF. So, to model the interference in a cable, we can replace wires by transformers. Here's what it's going to look like. Note that in a symmetric circuit, we have transformers for both conductors, while in a non-symmetric, only for one. Why? Doesn't interference affect the shield? Yes, it does, but it's really insignificant because the shield is grounded. In some situations, say when a printer is connected to a computer, shielding will be grounded at both ends of the USB cable. So, we will model interference by feeding primary coils of the transformers signal from the generator. Let us first take a look at what's happening in the non-symmetric circuit. The battery voltage is 3.7 volts. The oscilloscope is set to DC mode, and top of the screen corresponds to 5 volts approximately. I am shorting the circuit, and we can see the scope show battery voltage because DC can pass through the transformer as though it were a wire. Now let us attach the generator. It's set to 2.5 kHz sine wave. The moment we do, we can see the waveform appear on the scope. This is our interference, which, having been induced on the central wire of the non-symmetric cable, successfully made it to the output of the circuit. Let us fiddle the frequency a bit to make sure it is actually our interference. Yes, it is. Let us switch generator polarity. As expected, it does not affect the signal in any way. Now let's take a look at the balanced circuit. We got two identical transformers here wired both at the negative and positive wires of the battery. Interference in a symmetric cable must affect both wires, so to model that, we must feed generator signal to both transformers. But first let's try to engage them separately to make sure our circuit is working. Number 1. Working. Number 2. Working as well. Now let us wire both transformers' inputs to the generator and see what happens. We can see interference disappear. Of course, if we amplify the signal, we will see the interference, because our transformers are naturally not strictly identical. Same thing happens in a real balanced cable too. But the interference is so small that it's really unnoticeable compared to actual signal passing through the cable. Let me switch the polarity of one of the transformers so you can see there's no cheating here. Guess what just happened? The interference is now doubled. So basically, that's what balanced cables are all about. Both signal lines are equal and have no galvanic connection to the ground or shielding of the device. The signal, with the help of the inverter, is transmitted in opposite phase, as in our experiment: positive battery line, negative battery line. Interference, on the contrary, whether capacitive or electromagnetic, acts in phase and in the same polarity on both conductors. So, to decode the signal, a differential amplifier is installed at the output of the circuit. It basically subtracts voltage at one conductor from the voltage at the other conductor. So if the signal, for example, has potential of +2 and -2 volts, the result of subtraction will be 4. An interference having potential +3 volts on both conductors will thus have a resulting value of 0 volts. And our transformer experiment confirmed this. Despite the fact that the interference EMF is generated on both signal lines, it is not present at the output. And if we were to transmit digital signal, that's ones and zeros, they would have made it to the output in the same way, without disruption, despite common mode noise. And it is exactly this signal transmission method that USB standard uses. High level of D+ and low level of D- corresponds to logic 1. Logic 0 is coded with the opposite combination. For this to work properly, wires inside the cable must also be physically symmetrical. And what is the easiest way to ensure physical symmetry? Sure, just twist the wires. That is the reason why balanced cables use the so-called twisted pair, which is very popular in computer industry. It's used in the PCI Express bus, for example. This, by the way, explains why USB cables are used as extenders and GPU risers for mining rigs. Similarly, a balanced connection is used in UTP Ethernet cables. That means you, in fact, can make an excellent DIY USB cable out of a UDP or FTP twisted pair. An FTP cable can also be used to extend PCI Express risers. Also, you can make balanced audio cables out of UTP, FTP, and USB cables. So, Now we know that balancing two wires in a cable can be used as an effective protection method against external noise. However, there is only one logic line inside a USB cable. Like I mentioned before, the now obsolete LPT port had a total of 8 lines. How does a computer communicate with USB devices using a data bus consisting of only a single bit? As the name implies, USB is a serial bus. Serial data links have been used in computer industry for decades. Their obvious advantages are reduced production costs, low pin count, and simplified circuitry. So serial communication is very popular. It's utilized by PCI Express and SATA buses. Car industry uses it in CAN bus, and I2C and SPI serial buses are widely used in mobile devices. In a serial bus, before transmission, data bytes are broken into bits, which are then transmitted one by one. On the receiving side, respectively, these bits are reassembled and restored into bytes. Despite its apparent simplicity, this method has a number of nuances. Because USB, unlike I2C for example, does not have any dedicated physical synchronization lines, measures must be taken to inform the receiving party which exactly bit is being transmitted at a particular time. It's obvious that both parties must at least run at the same frequency, but in real life, it's not enough. So one-bit buses often use binary coding scheme known as NRZI, which stands for non-return to zero inverted. In NRZI, bits are represented by a transition of physical levels rather than constant levels. So, if we need to transmit a 0, we just invert the output line, no matter what its state is. If we need to transmit a 1, we do not change the state of the output line. This coding method serves only one purpose: to add additional edges and falls to the transmitted signal, using which the receiving party could easily synchronize with the transmitting party. This method, however, also has an obvious flaw. It may occur that at some point the transmitted data consists entirely of ones. As a result, the bus will freeze and synchronization will be lost. To get around this problem, a technique known as bit stuffing is used. If the data transmitted contains 6 ones in a row, a dummy, non-informational 0 bit is inserted into the stream. The receiving party is aware of this rule, so having received 6 ones in a row, it discards the bit that comes immediately after. The dummy bit, however, creates an additional edge in the waveform, which allows the receiver to keep in sync with the transmitter. It's also important to note that after 6 ones, a dummy 0 bit is always inserted, even if a real 0 would follow in the original data stream. Otherwise, the receiver would get confused, unable to distinguish between them. As a result, using NRZI's serial encoding, the host and USB device can exchange data over a bus that's only 1 bit wide. However, on the USB bus, bidirectional data transfer is also possible. Naturally, it can only occur one direction at a time. So for this to work properly, both parties must negotiate a protocol. Negotiation starts immediately after a device had been inserted into the USB port. In order to not miss this event, the host continuously monitors voltage of D+ and D- lines relative to the ground. The USB device, on the other hand, contains a 1.5K resistor wired between one of the data lines and an internal supply of 3.3 volts. So, once the device is inserted and the pull-up resistor is detected, the first thing the host does is pull both data lines low. But I just told you that the D+ and D- signals always have the opposite state because it's a symmetrical line. That is true, But this non-standard, seemingly erroneous state of the data lines is used to signal the device that the host sends a reset signal and the device must initialize itself. Once the host gets confirmation from the device that the reset command had been executed, it sends its very first query, whose purpose is to find out the maximum data packet size supported by the device. In programming, a data block of a fixed size is called a packet. Splitting data into packets is very natural in computers. Both computer memory and storage devices are organized in pages and sectors, and it's convenient to access them in this way. In telecommunication devices, packet size is related to the amount of buffer memory available and the speed at which data is processed by the CPU. So such request from a USB host really does make sense. As the device replies with its packet size, the host sends the initialize request again. As we already know, it's possible to attach more than one USB device to the host system. And if USB hubs are used, in theory, their maximum number can be 127. So how would the host differentiate between them? How would a particular USB device know the host is trying to access it? For that purpose, USB protocol implements addressing. After insertion, initially all USB devices must respond to address 0. However, after obtaining packet size, the host assigns a new individual address to every USB device attached. The address is basically a randomly generated number, but it remains unchanged while the device is inserted into the same USB port. Now that the USB device is initialized and has a unique address on the bus, the host starts actively communicating with it, trying to get as much information as possible. It requests device name, its class and version, a unique ID assigned by the manufacturer, serial number, etc. At this point, the device is considered initialized but not configured and can only respond to simple requests. Having obtained all this information, the host, based on the vendor ID and device ID parameters, launches the software driver necessary for the device to operate. If it's the very first time the device had been inserted, the user is prompted to submit the distribution media for the driver to be installed. And by the way, the vendor ID and device ID are the unique identifiers that absolutely all computer devices possess, not necessarily USB. Video cards, for example, also have them. And it is these parameters that Windows relies on when it tells you, for example, that the driver had not been loaded or does not work properly. So the host starts the driver, which sends the set configuration command to the device. After a confirmation had been received from the device, it is considered configured and ready to run. While the USB 2.0 standard has only a single data line, it supports full duplex mode, which means the data can be sent and received at the same time. Well, not literally, of course, but in digital data transmission, duplexing technique had been used for many years. The idea is that the data link switches between transmit and receive modes at fixed intervals. This creates two independent virtual channels for the end user, providing the illusion of simultaneous two-way communication. In USB standard, the switching occurs every 1 millisecond. A similar technique is used in mobile communications. Both parties can speak and hear each other simultaneously, while a single physical channel is used. That, of course, introduces a minor delay to the signal, but in most cases it's unnoticeable. Interestingly, the USB 2.0 standard also originally included the OTG functionality, which stands for on the go, and allows some native slave devices, like smartphones, to act as host. For this to work, you need to insert a special OTG adapter into smartphone's USB socket. As a result, your phone will be able to work with a mouse, PC keyboard, USB flash drive, and even a printer. Naturally, the OTG host can also power and charge the slave device. There's a YouTube video where a 5-inch USB floppy drive is connected to an Android smartphone. The disadvantage of the OTG mode is that the phone's USB socket is occupied, which means it won't be able to charge. It will, however, charge the slave device. Okay, so we've just discussed USB 2.0. But today it's almost obsolete, because it has been superseded by USB 3. How is 3 different? Well, you probably know that new generation ports, cables and devices can be recognized by blue connector color. And it appears they are pretty much the same, at least from the A connector side. In reality, it is not the case. USB 3 is much faster because it uses 2 additional twisted pairs to transfer data. One of them is responsible for sending, the other one for receiving. The protocol itself has not undergone any fundamental changes, while the decision to separate the receiving and sending data streams was sort of reasonable and expected. The original data link, the green and white wires, is also present in USB 3 for backwards compatibility. The B-side connectors have been updated and now look like this. And of course, the new USB-B socket can accept legacy B-type connectors. The latest update to USB 3 is the USB 3.2, which was released in 2017. Its key feature is the USB Type-C connector, which supersedes the USB Mini and USB Micro, providing a data link at USB 3 speeds. We can say it's the most progressive connector today, which can also work as USB-A. It's nowadays present at most motherboards sold. The most notable feature of Type-C is symmetric design that allows it to be inserted both ways. This is implemented by mirroring pins on both sides, so the total count of them in a Type-C is 24. So all devices that support this socket must also possess a dual set of data lines, since it is not known in advance which side the user will plug it in. Type-C also supports charging voltages higher than 5 volts. This delivers more power over the same wire gauge and allows for faster charging times. The standard is called power delivery, and I have a separate video on that. In August 2019, USB 4 was announced. The innovations that await us are really stunning. In addition to supporting the USB-C and power delivery standard, USB 4 will provide DisplayPort and PCI Express tunneling. It means that USB will be fast enough to work as a video output and will allow to connect expansion cards. The port will get as fast as 40 gigabits per second. With speeds like that, it will be able to compete with Ethernet and will probably replace it in the future. And finally, let me bust one popular USB myth. You have probably come across a Windows message, USB device not recognized. Most people tend to think it's caused by a missing or incorrectly installed driver. In reality, it's not the case. It's actually what it says. The host is unable to detect what you have inserted. Here's a little experiment that demonstrates it. I will connect a 1.5K resistor between the D+ and 5 volts lines. And here comes our message. There isn't anything in the USB port. We just attempted to trick the host. Naturally, having sent the initialize command to a non-existent device, the host got nothing in response. So it reported to the operating system that the device was not functional. Hence, the error message. In real life, you can see it when the USB cable is too long, or is of poor quality, or the connector is dirty or wet. What you should try in this case is clean the connector or move it to another USB socket, preferably the one on the motherboard itself, on the back of your computer. Wait, how could the cable be too long if it's factory manufactured? Aren't the folks there aware of production standards? The problem is, USB cables are mostly China manufactured. Very often, they do not meet the requirements. For example, this particular cable has no shielding, and the signal wires aren't even twisted. Obviously, it won't work with connections longer than 1 meter. A DIY USB cable, on the contrary, if properly made out of an FTP cable, can reach 10 meters in length. The reason you have to use FTP and not UTP is because it has better shielding that's more noise-proof. And that would be it for today. If you like this video, please give me a thumbs up and subscribe to this channel. And if you wish, you can support me by sharing this video in social media or by dropping some Bitcoin or Ether to my wallet. The links are in the description. This was Mattino. I'll see you later.